session. The speaker is Juan Parrondo, and I think we can just start.
Okay, thank you, Stefano. Can you hear me? Yeah, okay. So thank you, and thanks also to the organizers for inviting me and also for putting up this very nice conference. I'm learning a lot, and it's been a great experience. So I will talk about a problem that Edgar and I started like many years ago, like more than 10 years ago, which is precisely the estimation of entropy production. So it's very, even though Christian Miles doesn't care about estimated entropy production. But it's a problem that, well, we have heard Felix talk, and today Gilly Bisker will talk about this, and tomorrow probably Udo Seifert will talk about this. It's a problem that we are addressing from different points of view, different strategies. Our strategy at that time, and more recently, I've done work with Jordan, Gilly, and Iñaki Martinez. The strategy is always to estimate entropy production with partial information using irreversibility of signals. So how irreversible is the behavior of a process or the data that you collect from a process. So this is the principle that we are going to use all the time. And I will show you the different techniques that we have developed to quantify this irreversibility. But before, also I want to do some, to present some thoughts on the limitations of this strategy. And this is the outline of the talk. Yes, soon.
But do you believe, do you somehow work in a context where you believe that there is actually a God-given actual objective entropy production, and you want to know it, or yeah. What? So you believe in an actual entropy production?
Yeah, objective, I don't know if you want to enter into the problem of the definition of entropy. We are always in the realm of, let's say, thermodynamics with a local equilibrium. So entropy production is well defined always.
So local equilibrium.
Local equilibrium. You need, I agree that to define entropy production, you need local equilibrium. Otherwise, it's not possible. This is my opinion, but this is another question, completely different. So, why we are interested in this problem, and especially in biology, because in biology, sometimes you have access to just partial information of the system. Felix has told us, and also Pascal on Monday showed very nice examples of this situation. I have this cartoon where you go, you see this car behind the bushes, and then you can think that the engine is not running, and if you get more information, more degrees of freedom, you realize that the car the engine is running. So one question is, if I only have this information, can I get from the fluctuations or from the behavior of the car? Well, this is fluctuations are very small, but can I get, is there any signature of the non-equilibrium nature of the process in these fluctuations, in these partial fluctuations? This is the key question, which is practical, but it's also fundamental, because it's telling you what are the signatures of non-equilibrium. And this is what I think all the approaches are very interesting, because they tell us something about the nature of non-equilibrium. So this is the idea. This is the problem. But let me also, so the idea is always that we have partial information about the system. But there is some confusion in the literature. Well, not some confusion, but there are different ways of considering partial information. When you have a system like that, suppose you have 2 degrees of freedom, what we mean by partial information is very easy. It's just that we cannot measure one of the degrees of freedom. So we have access only to, for instance, here, x, And this is what we can obtain in the lab, the trajectory of x as a function of time, and we miss y. This is essentially what happened in Pascal experiments. So there are other possibilities, like maybe you can force the system, like what Felix showed us, and Pascal also showed us on Monday experiments where you can combine forcing and spontaneous fluctuations to verify or to check the validity of the fluctuation theorem, which is a signature of non-equilibrium. But this is the typical situation. When you have a kinetic models, like molecular motors or some chemical networks, things are more complicated. For instance, some people has considered, there are many papers by Takahiro Sagawa, Matteo Polettini, and recently by Edgar and another paper by Udo, that they consider that the information available to the observer is the statistics of transitions. So your observer is placed here, and the observer can see when the system jumps from B to A or from A to B, but ignores the rest of the dynamics. This is a possibility. Another possibility, which for us was more natural, but I think it depends on the experiment. Another possibility is that you miss some state. For some reason, you cannot observe this state. And in this case, for instance, if you have a state B, small b is hidden, this could be a trajectory of your system, no? It's making jumps from the different states, but you miss B. So you don't know really what is happening between this, in this interval of time, no? Between this state and this state. And also there are different possibilities for that. One is to imagine that you have detectors, like in a baseball field, you have detectors in each observable state. And you compute a transition when the system reaches the observable states. So in this case, for instance, the system is in state B, and you compute the transition when you detect that the system has jumped to C. So this is the decimated trajectory that you get if you have this approach. And maybe this is very technical, but it has some fundamental issue, which is that by doing so, you can induce a irreversibility, and a spurious irreversibility. So the initial signal here is completely reversible. You see it's invariant under reflection, and the red curve is not. For instance, if here you have, let's say, 1 unit of time before you go down, and when you go in this direction of time, you have 2 units of time before you go down. So you induce some spurious irreversibility that has been pointed out by Hartig and Godek in one paper, and also in some comment to our work as well. We have a different approach. Our approach is that if you have some state that cannot be observed, it's because you lump this state with other states, so you cannot distinguish between capital B and small b. And in this case, the trajectory is like that. It's more consistent because here, whenever you are in small b, your observed trajectory is in capital B. So it is, let's say, it's a 1-to-1, not 1-to-1, but it is local in time. The decimation is local in time. The partial information, the information that you miss is local in time. So, and why we think that this is, well, as I said, I don't want to make a case of which one is better or not, but we have in mind this type of situation. For instance, a molecular motor, where you have internal states, and but you measure only the position, which is in many experiments, single molecule experiments, you only measure the position. You cannot measure the ATP consumption or things like that. In this case, what happens is that if the motor has some internal states, you lump, let's say, you identify as this, you only have access to the position. So let's say that when you can serve only 1 degree of freedom, this is the most natural situation when you lose information. So this is as to clarify what we mean by missing information. In this case, we are always dealing with stationary states with no forcings. So it's a steady state. So it's a bit different than what Felix told us this morning. Okay, so now let's go to the principle, the main idea behind our techniques, which is the irreversibility, quantifying the irreversibility of a signal or of a trajectory. And it's based on a very general result that we derive with Chris Vandenbroek and Ryoichi Kawai, and that relates the entropy production in a process with the Kullback-Leibler divergence or Kullback-Leibler distance between the trajectory, one trajectory, and the reverse trajectory. I will not present the derivation of this result. It's not very difficult. It's a kind of consequence of a fluctuation theorem. But it is not a fluctuation theorem because this is the average entropy production, so this is the real entropy production. And this is the Kullback-Leibler divergence, and this is the microscopic trajectory and reverse trajectory. And the definition of the Kullback-Leibler divergence is this one. Is rho log of the ratio between the two. For those of you which are not familiar with the Kullback-Leibler, it's a fantastic concept from information theory. It's called relative entropy, but I avoid this term because I avoid to use entropy for this kind of concepts. The Kullback-Leibler divergence is defined for any pair of probability distributions, in this case P and Q. It could be the probability distribution of a single value, of a random variable, of a stochastic process, or whatever. And the main properties is that the meaning is that it's a measure of the distinguishability between P and Q. Actually, there is a theorem, very nice theorem, that tells you if you have two probability distributions and you don't know which is the probability distribution of a series of data, and you receive this data from a source, and you don't know if the source is generating data with P or Q, D is related with the number of data you need to distinguish between P and Q. And Edgar has a lot of work with Frank Jülicher and on the decision time and the relationship between the Kullback-Leibler and the decision time to decide if your data come from P or Q. Yeah.
I'm wondering why the proportionality constant is KB, not 2 KB or half KB.
Well, because it's a theorem. I mean, it's a good question, and well, it's because well, I can tell you just the proof is not hard, but you can identify here in the Kullback-Leibler, here is minus the Shannon entropy of P. So when you put this, when you expand this Kullback-Leibler distance, you get the Shannon entropy of the initial condition and the Shannon entropy of the final state. And it turns out that the Shannon entropy, if the system starts in equilibrium, there are some hypotheses here. You have to start in equilibrium and so on. But if you start in equilibrium, KB P log P is the thermodynamic entropy. Is the for systems in equilibrium. For a system out of equilibrium is different. For a system in equilibrium, this is. So this is why it's KB. And this is going to be important. Okay, this is a measure of the distinguishability of two distributions. When you put here the probability of something that occurs, of the forward trajectory and the backward trajectory, the Kullback-Leibler divergence is just a measure of the irreversibility. It's a quantitative measure of the irreversibility. What this is amazing is that this quantitative measure of irreversibility is equal to the entropy production. But this is, as I said, you can prove this for Hamiltonian systems, even in quantum mechanics. So this is very general. One property which is important is that it is always positive, and also that if you have a system described by two variables and you miss one of the variables, then the Kullback-Leibler divergence decreases. And this is natural. The Kullback-Leibler divergence is how distinguishable are P from Q. If I have less information about my system, then this becomes less distinguishable. So this is very important in the following, this inequality. Okay, so if we apply this, by the way, this is equal, and it becomes, if I reduce my information, this is a microscopic trajectory, so I completely, all the momenta and the positions of my thermal baths and so on. So if I coarse grain or I miss information from my system, this will become an inequality. But actually, if in your trajectory you include all the non-equilibrium magnitudes, we should define what is a non-equilibrium magnitude, but all the magnitudes that are not really in equilibrium, like you can get rid of the fast, for instance, the fast variables which are equilibrated and so on, then this stays an inequality. This is why this is also an inequality for master equations, for Langevin equations, and so on. You can prove it for Hamiltonian equations, but it is also true for Langevin equations and for master equations. When you have a stationary trajectory, this in principle, a stationary trajectory means that you have some experiment and you record some data in time. So this is your time series, your data, and you can, if the time series is stationary, you can obtain the frequency, the probability to observe some sequence of data. And if you apply the Kullback-Leibler divergence applied to this data is this one. And if you miss variables which are out of equilibrium, you get an inequality. And if you include all the non-equilibrium magnitudes, you get an equality. So in principle, this can tell you the entropy production of your experiment, of the process in your experiment, or it can give you a bound. We call this bound the KLD bound to the entropy production, okay? And this is the principle. This is the idea that we have behind. So let's compute the KLD, the Kullback-Leibler divergence for Pascal's data or for Felix data and so on. Okay. This formula is fascinating somehow because the left-hand side is physics. Well, maybe you don't like entropy production. It's the heat, dissipated heat. It's the ATP consumption in a biological system and so on. And the right-hand side is just, depends only on the data. So you can apply this in principle to the results in the league, in the football league, or wherever you like. So, and this tells you what is the minimum entropy that you need to produce to have this behavior or to have this irreversibility. So I think, actually, Landauer's principle is a kind of it's a special case of this. You cannot generate any data. I mean, if you want to generate some data, you need to dissipate some heat. This is what the formula is telling you. But it has limitations. It's very nice. And as I said before, this problem of estimating entropy is interesting because of practical reasons, like Felix told us or Pascal, but also for fundamental reasons, because we learn what is fundamental things of statistical mechanics. Okay, so, but it has, before the limitations, I will show you that it has a lot of limitations. Let me relate this formula with typical irreversible thermodynamics. If you apply this formula to sequence of two data, let's call this S2. So this is you have to calculate this and take the limit n going to infinity. So you look at words, and you look at the frequency of words, and you increase the length of those words. If you look at words of two letters, of size 2, you get this, and you get this formula. And this formula is known since the 20s. So it is this, you can write this as a current times the log of the jumps, the probability to jump from I to J and J to I. And this is an affinity. So this is just a current times an affinity, or also the heat. So what you obtain with two data is just what we know in from irreversible thermodynamics. Felix wrote this equation before. So it's nothing new. And moreover, if your process is Markovian, it turns out, I'm sorry. If your process is Markovian, it turns out that in this limit, you don't need to go to n going to infinity, because any probability can be factorized into a probability of pairs, of jumps. So you can compute the Kullback library divergence just with words of size 2. So for Markov chains, this beautiful formula doesn't tell you anything new. It's what people knew since the 30s or since the 40s, that like entropy production is this. Okay. But also, if you have a Markov chain, if the current is 0, then the entropy production is 0. And this is interesting, that if your prediction, so if this formula predicts 0 entropy production if you don't have fluxes. So if you go back to my cartoon of the car, or you see a molecular motor at stall force, then this formula tells you that the entropy production is 0. Even though the motor maybe is consuming ATP, like my car in the park is consuming gasoline. Okay. So our idea is that when you have partial information, your system is no longer Markovian, so you can apply this formula, and maybe, and I will show you that there are situations where you can do it, you can detect and bound the entropy production even when in the absence of flows. We thought that really our technique is powerful, or is important when you don't have flows, which is like in Pascal example, because the hair cells are confined, you don't have flows. You don't have any flow. Okay, but there are limitations, and one can see the limitations immediately, and also the limitations tells you something about irreversibility. The first one is that by losing 1 degree of freedom, you can lose everything, and this is suppose that you have a limit cycle. You can add some noise. I didn't add noise because my program to draw things, I only know how to draw circles, but you can add some noise here, and you can have this trajectory. Actually, this is what we think we have in the hair cells. If you add the position of the tip plus, I don't know, the calcium concentration or something like that, you will have something like that. And but now suppose that you miss Y, and you plot the behavior of X. X is just sinusoidal, which is reversible. It's completely reversible. So by missing 1 degree of freedom, you can lose a lot. This is, and we knew this from the very beginning. And in the case of limit cycles, for instance, the technique can tell you something only if the limit cycle is not symmetric. So it is very bad. I mean, another limitation is that in this formula, I mean, this is a log, and these are probabilities. So this is of order 1. So the bound that you can obtain is of order k. This technique cannot predict entropy productions of the order of 10 to the 4, like Felix showed us this morning. Because, I mean, if you want 10 to the power 4 times k, you need that this is the exponential of 10 to the time, you need, and this is of order 1, you need that the reverse must be very unlikely, must be exponential of minus 10 to 4. So which is, you will never see this in a trajectory. So because our technique is based on irreversibility, you need to observe the reverse process. If you don't observe the reverse process, you miss everything. And when the entropy, this is nice also because we have this quantitative relationship between irreversibility and entropy production. When the entropy production is macroscopic, is 100K or even 10K or 10 to the 4K, then the process is completely irreversible in the sense that the reverse process is impossible to observe. Actually, I like this philosophical idea that for systems, for Markovian systems, we can measure this as he divided by t. So we can really, in macroscopic irreversibility, we can measure, by measuring heat, we get the probability of something which is impossible, which is, well, it's interesting. How can we get how can we measure probabilities which are 10 to minus 5, okay? Anyway, these are the limitations. So you can think that the technique, this is why I want to say something more about that. That in the first case, the first limitation, you see, this is completely reversible. But if I show you this, you will say, this is not an equilibrium system. This is a non-equilibrium system. So we are missing something also which is fundamental, which I think the TUR and probably Felix technique probably incorporate. That you don't, the signature of non-equilibrium is not just irreversibility. It's also the nature of the fluctuations here. You see this, and if the system there is no inertia in the system, you say this is not an equilibrium fluctuation, okay. Okay, so now the techniques. We have applied 3 techniques to quantify the Kullback-Leibler divergence. I will show you, not in very detail, the first 2. Also, it depends on the system. So the first thing we tried with Edgar 10 years ago was brute force, was to apply this formula like it is here written. But we proved the main concept, which is that in absence of motion, you can detect entropy production, and this is where we were so happy. So we had this situation like the situation with the car. We had a model, the most basic model for a Brownian motor, molecular motor with a flashing ratchet, and you know that the motor moves, but if you oppose a force against the motion of the motor, at some point the motor stops, but it still fluctuates. So this is called the stall force when the motor stops. And of course, the classical irreversible thermodynamics tells you that the entropy production is 0. You remember that the classical irreversible thermodynamics is the Kullback-Leibler just with 2 points. So it tells you that it is 0. These are trajectories. And it's not easy to see here the irreversibility. But if you use this formula with 3 points or 9 points, you get not very close, but this is the actual entropy production. This is log scale. But you see, the stall force doesn't, well, in linear scale, you can see a bit that the stall force plays a role. But here in log scale, you see that you can, the entropy, the Kullback-Leibler, which is a measure of, so the irreversibility is not, the stall force is not visible, which is amazing. I mean, when we saw this for the first time, you know, it was, so we can detect, because the system is non-Markovian. Here, as I said before, the missing information is the internal state. Here we only, so it's more or less what you have in an experiment, that you see the position of the motor only. And from the statistics of 3 points or 9 points, you can see the irreversibility and then the entropy production. Okay, we were very happy. This was years ago. And then, but of course, brute force, here we apply brute force. Brute force is to generate trajectories, look at words of 3 of length 3, oops, of length 3. So for instance, you can look at when the system is 0, 1, 2, 0, 1, 2, 0, 1, 2, you compute the frequency of this word appear in your time series, and you compute the same for the reverse, 0, 1, 2 or 2, 1, 0. And then you put it, you plug this in this formula, and then you obtain this. But can you imagine that for 9 points, it was difficult, because the number, here you have 3 states. So it's 3 to the power 9, the sample. So you start to, you need a lot of statistics. So brute force is impossible, and can you imagine this for, even for discrete, for continuous systems. So for continuous systems, Edgar developed this nice idea that I think Pascal explained it better than me here, that you have a time series which is non-Markovian, with a lot of correlations and so on. So it is impossible to calculate this Kullback-Leibler divergence. But the idea is to transform this time series into a white noise, And this can be done. It's something called whitening transformation, that we learned that it is in the literature before we thought of that. And then, because the Kullback-Leibler divergence is invariant under transformations, you can now calculate the Kullback-Leibler of the 2 white noises, which is very easy. So this was a very nice idea, and I think Pascal told us this very well. But of course, we have the limitation that the only irreversibility that we can detect is of order 1, and the entropy production is of order k. So in the hair cells, probably is 10 to, is 100k, no, or even more. So this is, the bound is very far from the real value, but it's true that we could detect active, we could distinguish active versus passive process like that. And the last technique, it's not a technique, it's just in those years we developed a kind of skill to detect, to how to detect irreversibility in time series, so in different time series. So we realized that in situations which are important for molecular motors, which is like that, when you have a molecular motor in the stall force, your motor, this is here, this big ball, doesn't move in average. So the probability to step upwards and a step downwards is one half. But you have continuous time. So the time to make a step can be different. And this was the idea, to use the time between steps to detect irreversibility. And this cartoon explains the idea in just 1 second. Here you see that you have a trajectory, and even though the system doesn't move, so you cannot detect, if you just look at the states, you cannot detect any irreversibility here. By looking at the time, you detect immediately an irreversibility. This trajectory is not invariant if under time reversal. Why? Because in the forward trajectory, you have to wait 2 seconds when you are to go down. No, you are always 2 seconds, go down, 2 seconds, 1 down. 2 seconds, go down. And to go up, you need 1 second. 1 second, 1 second, 1 second, 1 second. When you reverse time, it's the opposite. You will wait 1 second to go down, and you wait 2 seconds to go up. Well, it's as simple as that. So we realized that, and we said, oh, this is interesting, because remember that our dream is to detect entropy production in the absence of flows. So here we can detect entropy production just by looking at the waiting time distribution. And this is what I did with Jordan, Gili, and Iñaki Martinez in this paper, which is an intercommunication paper. And I will show you more or less we need to use waiting time distributions. For waiting time distributions, there is a fantastic concept which is the semi-Markov chains. Semi-Markov chains, which are very useful in molecular motors, because it is they are Markovian, So here you have the simplest one. It's a Markovian system if you look at only the states, but it's not Markovian if you look at the time of the steps. Actually, semi-Markov chain is defined by the probability, the waiting time distributions. These are called, or transition time distribution. This is a transition time distribution. This is telling you the probability that the transition from 1 to 2 occurs at time t, when the system arrived at state 1 at time 0, at t equals 0. So you can you can define different things. And the nice thing of the semi-Markov chains is that if you have a real Markov chain is when you don't have any memory, then the jumps are Poissonian. We call it Poissonian events, and the distance between two Poissonian events is an exponential. So this is a necessary and sufficient condition for a semi-Markov chain to be Markov. This must be exponential. And semi-Markov is when the trajectory of the states is Markovian, but if you include the time, then it's not Markovian. So it's a very nice case of non-Markovian process, but that you can work with it as if it were Markovian, except for the time. And for motors, it's very interesting because for motors, you usually this is what you have. Let me explain first. For motors, for instance, you can have a motor with internal states, and then you can compute the time to go from here to here to observe a transition is not going to be exponential because the system can explore all this, and then this will not be exponential. So this is the semi-Markov processes appear when you have models, kinetic models of molecular motors. And in principle, the semi-Markov model, the semi-Markov chain appears when you miss information in the sense that I discussed at the beginning of the talk. So, the idea is to detect irreversibility, as I present in my cartoon, in these cases. And this is what we obtain. This is a formula, exact formula of the entropy production in a semi-Markov chain. It has, the nice thing is that it has two terms. The first term is we call it affinity because it's the typical one of let's say it's the one that I presented before is the irreversible, is current times affinity. So this is the typical one, which is 0 if you don't have flows. And the new term is this one, which is a term that here you have the Kullback-Leibler divergence between the waiting time distribution. So if you have irreversibility in the waiting times, then this is different from 0. And this can be different from 0 in the absence of current, okay? So this is what we have for semi-Markov chains. Okay, and now just the results. For instance, for a molecular motor like the one that I showed before, here you have the model. This is the position. You have a force here, and you have internal states. And the only information you have is the position. So this could be a trajectory of the position, and here you have the interval of times where the system is in this state, but you don't have this information, so you only have information of the position. And you see that if the motor is in equilibrium, the waiting time distributions are indistinguishable, but you can have a non-zero, an irreversibility when the motor is out of equilibrium. And this is the entropy production. This is the green curve is the entropy production predicted using irreversible thermodynamics, which is 0 at the stall force. These are different values of delta mu. Delta mu is the fuel. And this is the red curves are the real entropy production, and this is our estimation, which is, in this case, the stall force. This is very close to equilibrium. And, but here you can have, well, here you have a better idea. This is the entropy production predicted by irreversible thermodynamics. This is the real one, and this is the one predicted with our method. Okay. So I think we have for hidden network, but I think I will finish with this. Let me summarize that I've shown you that that time reversal asymmetry reveals entropy production. We have I've shown you different applications or techniques, and there are other applications. For instance, Jordan and Nikta Factory has done a very nice work on using the Kullback Leibler in intervals of time, so to detect in which scale of time dissipation is occurring. And this is very interesting. And tomorrow you will see more, or today with Gilly, more information if fluctuations reveal something about the dissipation that is taking place in the system. And also, I want to mention that it is also interesting the other way around. For engineers, especially in nanoscience, if you want some, or for evolutionary biology, if you want some behavior, what is the minimum, like, let's say you want a clock or an excitable system like a neuron, what is the minimal entropy production to have this behavior? I think this is also a great question, and I thank you for your attention.